In this video, we will examine projectile motion in the case where the object moving through the medium experiences a drag force that is linear in the velocity. Well, alright, we start out the usual way. We draw a free body diagram. There are only two forces acting on the projectile once it has left the launch point. There is the force of gravity acting straight down and the drag force, which is directed opposite to the velocity. Since these are the two forces, the net force will be somewhere between them, and that will be the direction of the acceleration. All right, so we have the net force vector is equal to the mass times the acceleration. Net force can be written as drag force plus gravitational force equals ma, and we can write the gravitational force as minus mg y hat. We can write the drag force as minus b v vector. So that shows us that it is linearly proportional to the velocity and it is in the opposite direction. And all of this is equal to ma. We now split it up into x and y components. In the x direction, there is no gravitational component, but there is a drag force component. So we have minus bvx is equal to max. And in the y direction, we have minus mg minus bvy equals may. So now we're going to focus on the x component and see what we can do. So we started out with minus bvx equals max, and we know that this is the equation of motion in the x direction and that we will want to solve it. So first we rewrite it a couple of different ways to see which is the easiest version that we can attack. So we could write it all in terms of x and derivatives of x. So we'd have minus bx dot equals mx double dot. But that involves a double derivative and a single derivative, and there is no actual plain x in this equation. So in fact, it would be better to write this as minus bvx equals m times vx dot. So now we have unknown function vx and its single derivative. This can be solved. Vx dot, after all, is just dvx over dt. And we can separate the variables. Our two variables here are vx and t. And so we move the constants and t dependent terms to one side and the vx dependent terms to the other side. And now we integrate. On the vx side, we end up with natural log of vx. And on the other side, we end up with minus b over m times t plus c1, which is an integration constant. We would like to find vx as a function of time, so we can get rid of the natural log by using an exponential, and so we end up with vx is equal to e raised to c1 times e raised to minus bt over m. But since c1 is a constant, e raised to c1 will be just some other constant, so we can write that as vx is equal to c2 times e to the minus bt over m. Now let's look at the y side. On the y side again, we rewrite the equation a few different ways to see which will be easiest to attack.
First in terms of the y's, but again we have the same problem. There is no actual y in this equation and we don't really want to deal with the double derivative if we don't have to. So we rewrite it in terms of vy. This again is amenable to separation of variables. We bring the vy dependent terms to one side and the t and constant terms to the other side.
Notice that to make life a little bit easier further down the line, I pulled out a factor of minus b so that I would get vy by itself over here, and then divided this term in parentheses over, and of course the dt moved over to this side. Again, we can integrate this, and much like before, we end up with a natural log, which we can get rid of by using an exponential. And so we have mg over b plus vy equals a constant c4 times e to the minus bt over m. Let us examine our solutions. In the x direction, we arrived at vx equals c2 times e to the minus bt over m. We would like to determine what the constant c2 is, so we look at initial conditions. At t equals 0, vx will be the initial x velocity. And so we have vx0. And on the right hand side, we would have c2 times e to the 0. But e to the 0 is just 1, so this is c2. So this fixes the constant c2 to be the initial x velocity, and so we have Vx equals Vx naught times e to the minus bt over m. All right, now that we have the solution in the x direction, let's check if this makes sense. What this tells us is that at t equals 0, the velocity is just the initial velocity. And then as time passes, this velocity in the x direction decays off exponentially. And this makes sense. The only force in the x direction is a component of the drag force. And so this will slowly leach away the velocity in the x direction.
We proceed along similar lines in the y direction. We would like to determine the constant c4. Again, we look at initial conditions. At t equals 0, we get mg over b plus initial velocity in the y direction equals c4. So that fixes c4. And we can rewrite our solution.
We have mg over b plus vy as a function of time is equal to mg over b plus vy naught, the whole term in parentheses, times e to the minus bt over m. We are solving for vy over t, and we can write this in two different ways. We can leave the exponential term as is and just have minus mg over b on this side. Or if we want, we could split up the exponential terms, have one term which depends on the initial y velocity and the other which has this mg over b term, along with a mix of 1 minus e to the minus bt over m. Again, let us interpret our solution. And why do we like having two different ways of writing it? Well, if we plan to take derivatives or integrate and so on with respect to time, then it's nice to have all the time dependence together in one term. But in fact, with the physical interpretation, it's slightly easier to see what's going on in this case. What we see here is that this term represents the initial velocity, which is going to, again, exponentially decay. Whereas on this side, what do we have? We have a 1 minus e to the minus bt over m. You might remember a similar type of function, for example, in the charging of a capacitor. And we know that that function, well, just like the exponential decay, looks something like this, decaying off to 0. 1 minus this exponential decay represents a function like this, which asymptotically approaches some value, which in this case it would asymptotically approach minus mg over b. So let's look at our solution. We have found the velocities in the x and y direction, and these are the equations. Let's notice a few points. One is that the argument of an exponential must be unitless. The reason being that we can always expand an exponential as a power series with an infinite number of terms. And if the exponent here had units, then each term of that power series would have different units. In order to avoid that, we require that this exponent should be unitless. That tells us that bt over m is unitless. But that means that, well, since t has dimensions of time, m over b must also have dimensions of time. And so we have a characteristic time, which we shall call tau. Similarly, we expect that only terms with the same units can be added or subtracted. If this exponential term is unitless, then we see we have units of velocity here. Again, this term in parentheses over here, this term as a whole is unitless. And so mg over b must also have units of velocity. And so we define mg over b is equal to v term, the terminal speed. Let us check our interpretation. These were the equations. We will consider the case where you have an object dropped from rest. In such a case, the initial velocity is 0 both in the x and in the y direction. So vx0 is 0, this whole side goes 0, and so vx stays 0. What about in the y direction? In the y direction, Vy0 is 0, this term goes away, and we have Vy equals minus V term times 1 minus e to the minus t over tau. This makes sense because as t tends to infinity, we have 1 minus e to the negative infinity. E to the negative infinity is 0, so this term goes away, and Vy tends towards minus V term. And if we think about it, if we drop an object from rest, and the situation is such that it can experience drag velocity long enough, then eventually it is still falling down in the negative y direction, so it has a negative y velocity, and it reaches terminal speed and stops at that speed. It doesn't accelerate any further because the gravitational force will balance out against the drag force, and the net force will be 0. And so it asymptotically approaches this terminal speed in the negative y direction. Let us examine the characteristic time tau again. So it's given by m over b, and we see that it is an exponential decay time constant. Again, these time constants were seen when we dealt with capacitors charging or discharging, or when we dealt with inductors having the current through them changing. To give you a reminder, we see that at t equals 0, Vx is Vx naught. After one time constant has passed, we have Vx is Vx naught times e to the negative 1, which is 0.37 Vx naught. So in other words, the velocity in the x direction has dropped to 37% of its initial value after one time constant. After two time constants, it's down to 13.5% of its initial value. And after three time constants, it's down to 5% of its initial value. This is an exponential decay. Besides the characteristic time tau equals m over b, we also had the terminal speed v term, which is mg over b. And notice that these two are not independent. We see that v term is just g times tau. Also notice that the value of tau tells us something about the importance of drag. If tau is very large, then it will take a very long time for the x component of the velocity to die down. So in other words, tau being large indicates a small effect from the drag force. Notice that as v gets bigger, the drag force gets stronger and tau gets smaller. This makes sense, it decays off faster. So we have found Vx as a function of time. Let's go on and find x as a function of time. We first rewrite the equation using our new constant of tau. Vx, of course, is just dx over dt. Here, to avoid variable confusion, I'm using t bar. And then I integrate both sides on the dx side from x naught, the initial x position, to our x as a function of t. And on the time side, we have from 0 to t. You can evaluate that integral. Vx naught is a constant, so we just have an integral of an exponential, and that gives us an additional factor here of minus tau. And so we are left with x of t minus x of 0 equals Vx naught times tau times, in parentheses, 1 minus e to the minus t over tau.
So how does that behave? As t tends to infinity, x turns to the initial position plus Vx naught times tau. Again, we have this charging capacitor type behavior. If we set the initial position to 0, instead what we have is asymptotically approaching this value of Vx naught times tau. Let us similarly solve the y equation to go from velocity to position in the y direction. And we simply rewrite the equation. We integrate both sides. There's slightly few more terms here, but in the end it is still just the integral of an exponential. And well, there's also the integral of a constant term. So we arrive at y of t minus y0 equals minus v term times t, minus, and then parentheses, we have some constants here, times this term in parentheses over here.
And we can rewrite that to y of t is equal to the initial y position minus v term t plus this whole term. Again, we see the sort of charging capacitor behavior here. As t tends to infinity, well, y0 is constant. And in this term, we see that as t tends to infinity, this term is going to go away. So we have a bunch of constants here. And then we have minus v term times t, but t is tending to infinity. So we are inevitably going to have a large negative term over here, which makes sense. Assuming it doesn't hit the ground, it continues to fall in the negative y direction with a constant terminal speed. And so the y position gets more and more negative. Since the physical setting is projectile motion, we ask, how can we find the time of flight? The projectile is launched at an initial position of y0, and we take its landing to be symmetric with its launching, so that it will land when its position at some time big T is equal to its initial position. And we say that at this point it's hit the ground and it has landed. So the time that it takes to do this is the time of flight, which we shall denote as big capital T. This gives us an equation that we can solve. Y of big T and y0 cancel out, so we have 0 equals minus v term big T, and so on. And in the exponential, again, of course, we replace little t by capital T over here. This is unfortunately a transcendental equation, which means that it cannot be solved in terms of standard basic functions like trig functions and exponentials and logarithms and so on. How can we solve it? Well, we could solve it graphically by plotting a linear function versus this exponential function and seeing at what point they satisfy this equation, which would be depicted by an intersection of graphs. We could solve it computationally. And indeed, these days that is fairly easy to do. But sometimes you don't have access to a computer that can solve this equation, or perhaps you are just interested in a perturbative case where you want a slight correction to your usual answer. So we shall look at a technique in which we will solve this equation for the case of a small linear drag effect. And of course our solution will be approximate, but is nevertheless insightful. A few points to note. T, the time of flight, and tau, the characteristic time, or the time constant for the exponential decay, look very similar. Don't confuse them. Right? Write them as distinctly as possible. Another thing to note is that the terminal speed mg over b and the time constant tau, which is m over b, are not independent. This is important when we start to expand our equation and look at the effects of small drag. We have to be careful exactly how we count small drag, and both these terms are related, in fact.
So we wish to find the time of flight when the effect of air resistance is small. A small linear drag implies that the exponential decay that happens is going to take a long time, and so tau will be very large.
Or in other words, 1 over tau will be very small. We return to the equation that we are trying to solve. We will solve an approximate version of this equation using the approximation that 1 over tau is small. And the idea here is that we will take into account terms of order 1 over tau, but we shall ignore terms that are of order 1 over tau squared. In other words, we are creating an expansion in terms of 1 over tau. We shall keep constant terms, we shall keep terms which are linear in 1 over tau, but we shall discard 1 over tau squared terms and smaller terms, because as we increase the powers of 1 over tau, they get smaller and smaller. To be precise, what we are really looking at is the ratio t over tau, which is unitless, and we are making the assumption that t over tau is much less than 1. All right, so how can we approximate this equation? Well, what is making it tough is this exponential here, so we can expand the exponential. Again, a reminder, we will keep only the 0th and 1st powers of 1 over tau in our expansion. But when counting powers of tau, we have to be careful because v term is equal to g tau. And so we will need to replace these v term terms by g tau in order to count powers of tau correctly. We replace v terminal by g tau and then expand the exponential. There are, of course, an infinite number of terms in the expansion of the exponential, but we will only keep the first few. How many do we need to keep? Well, remember we said that we would keep terms that were linear in 1 over tau. This would represent the lowest order approximation of the effect that air resistance has on the time of flight. All right. Well, no real change over here. In the exponential expansion, we might be tempted to stop at this term. After all, there's a t over tau right there. But then we remember that outside multiplying it, we have in fact 2 powers of tau. So if we want to be consistent, we will have to go all the way until tau cubed, right? When this term multiplies this g tau squared term, we will be left with 1 over tau. Now, of course, along the way, we'll be picking up some extraneous smaller powers of tau. We will discard those as we see them. We first simplify the terms in the parentheses. The 1 goes away, some signs change, and then we multiply out the terms. Expanding them further, we start gathering them by powers of 1 over tau. There are some constant terms. We have a vy0 times t. We have a minus gt squared over 2. Notice that the tau's cancel. We have some cancellations. We have minus gt tau cancelling with plus g tau t. So that brings us to these 2 constant terms. And then we have 1 over tau term. So we get one over tau term over here, minus vy0 t squared over 2 times 1 over tau. And we get another one over here where this tau cancels partially with the 1 over tau squared here. And we end up with a gt cubed over 6 times 1 over tau. All the other terms are of order 1 over tau squared or smaller. The O here, this is an O, not a 0. This is O for order, so of order 1 over tau squared and smaller. So we have a 0th order in 1 over tau and a 1st order in 1 over tau, or as I said more precisely in t over tau. We have simplified our equation and we would like to get the value of the time of flight t. We have agreed to throw away these extra terms. So we have a cubic equation, but we see that there is a common factor of t. We now have 2 options. One option is to factor it. We pull out a common factor of t, and what is left inside this parentheses is a quadratic equation which can be solved. So this tells us that the time of flight is either 0, which makes sense because that is the first time when the projectile is at ground level, or it is the solution to this equation. So we can solve this quadratic for t. However, that is a little tedious and doesn't give much insight. So we shall look at another method. What we do is we say that since the effect of air resistance is small, the time of flight should change only a little bit from the vacuum result for the time of flight. So T0 here represents the time of flight when there is no air resistance, and epsilon here represents the small correction that is made due to the 1st order effect of air resistance. We will insert this guess of ours, T equals T0 plus epsilon, into this equation, where, as I said, T0 is the 0th order solution and epsilon is a small correction of order 1 over tau. First, we determine the 0th order solution, that is, we determine T0, and the 0th order term gives us this equation, and that gives us that T is equal to 0, or this equation must be satisfied. We solve and get T0 equals 2 Vy0 over g, which should be familiar to you from projectile motion. We now return to the full equation up to 1st order. So this kind of iterative procedure is often used when you want to perturbatively solve an equation. You solve the 0th order and then take your guess and plug it back in, allowing for a small correction. Here is the full equation again, and we set T equals T0 plus epsilon, which gives us a bunch of terms. But we are only interested in the 0th and 1st order powers of epsilon. So this allows us to expand this and get rid of a bunch of terms. These terms do not depend on epsilon, they're the constant terms, and these depend on epsilon to the first power, and then we have some epsilon squared and higher power terms that we will neglect. However, we have to be consistent in our procedure of solving. We have dropped terms of epsilon squared or higher, and we have said that epsilon is of order 1 over tau, so we should drop terms that are of the form epsilon over tau, which allows us to get rid of these two terms. We also remember that t0 is a solution to vy0t minus gt squared over 2 equals 0. And this allows us to actually get some terms to cancel out. And so what we are left with is this equation. And we are trying to solve for epsilon, which is our correction to t0. We solve for epsilon and then plug in for the value of t0. We notice that this term gives 1/3 vy0, this term gives minus vy0. The vy0's cancel, we pick up some numerical factors, and we end up with finally this simplified term, which is negative. Putting it all together, we find that to our first order approximation, for small linear drag, the new time of flight is t0 plus epsilon, and our epsilon is a negative term, so in other words, the effect of linear drag is to decrease the time of flight, which is not surprising. We can pull out some common factors, and we end up with this expression. We would like to use this time of flight then to find the range, that is, how much distance is actually covered on the ground. To find the range, we use our time of flight in the x direction equation. So we are trying to find what is the new x position at the time when the projectile hits the ground again. So we have x of 0 plus this term, and we now have a value for t, but remember, our answer is only good up till order 1 over tau. So we must expand this and keep only terms up till first order in 1 over tau. We expand the exponential. We notice again that we have some terms out here. So if we want to keep terms up till 1 over tau, we in fact need to expand the exponential up till 1 over tau squared. And then multiply things out, discard the higher order terms, and finally we are left with this equation. We can plug in for t. This is the corrected new time of flight. This is our full expression. But again, remember, we only want to keep terms up till first order in 1 over tau. And we don't really need the correction over here because there's already a 1 over tau sitting out here. Gathering everything together, we see the original range and then the correction. And so we get that the new range is this expression. Let's summarize. We have the new time of flight, where we notice that the term outside can be written as tvac, the time of flight in vacuum, and the term inside, well, g tau is in fact the terminal speed, so we can rewrite this as 1 minus vy0 over 3 v terminal. And we have been making the assumption that the effect of the drag force is small, which corresponds to the assumption basically that vy0 is much less than v term. Similarly, for the range, we can write it like this, and we realize that we can write that new range as the vacuum range times this correction factor. Again, we are making the assumption that vy0 is much less than v term.